So truth and falsity of quantified statements. So I'm giving you this example. A, let D be equals to the set of 1, 2, 3, 4, 5. And you have this statement. For every x in the domain, x squared is greater than equals to x for any. So we're using a universal quantifier. Universal quantifier, and it's, you read it as for all, for any. Then I'm giving you this one as well. Let D be R, real number set, and consider the exact same universal statement. For every x in D, x squared is greater than equals to x. So which one of these is a true statement? Very well. So we have universal statements here. It says for any x in D, what is D? Okay, D is limited. D is given to us, the domain is given to us 1, 2, 3, 4, 5. So for any, I might select 1, you might select 2, another student might select 3, another one might select 4, the other one might select 5. So when you have a universal statement, you have to check for every element in that set. When you have a universal statement, to check its value, we need to check every member in the domain. So what's the meaning of that? We have to check for 1. 1 squared is greater than 1, of course. 2 squared is greater than 2, correct. 3 squared is greater than 3, of course. 4 squared is greater than 4, yep. 5 squared is greater than 5, of course. So definitely this universal statement with this domain is true. So this universal statement is true. Okay, now let us move on to the second one. We're using the exact same universal statement, but we're changing the domain. Okay. So I know when I have finite numbers of values in my domain, it's super easy to check each one of them. But here I have R. R is the set of all real numbers. All real numbers. How do we check each one of them? So in these cases, it's easier for us to try to find a counter example. Note that since R has infinitely many numbers, it is impossible for us to check each member. So what are we going to do? Instead, we try our best to find a counter example. Instead, we try to find counter example. But what is a counter example? It's a number in this domain that make this guy a false statement. So let's get back to algebra. How do we graph this? It says x times x minus 1 must be greater than or equal to 0. So here, if you form the table, x minus 1, and then x times x minus 1, here, this is 0, negative, positive. Here it is 0, negative, negative, positive. So it's going to be positive, negative, positive. So if you graph this, this is just a quadratic inequality. X times x minus 1. This is going to be like this. When your x is in between 0 and 1, it's going to be below x-axis. Oh, this is like this. So if you take any number between 0 and 1, any number between 0 and 1, make this statement a false statement. Make this a false statement. Well, you might say, hey, what if I take, let's see, a half? You write it this way. You say, there is a half in R such that 1/4 is not greater than or equals to a half. A half is a counter example. A half is a counter example. You can come up with tons of different counter examples. This is one of them. So this counter example tells us that because of this domain, this universal statement cannot be true. Well, let us investigate the truth and falsity of existential statements. So remember that for truth and falsity of a universal statement, we have to check every member, or we find a counter example. Truth and falsity of existential statement. So I'm giving you two examples. There exists a positive integer such that m squared, the square of that positive integer, is equal to that integer itself. B, let E be the set including 5, 6, 7, 8. And then I'm going to repeat the exact same predicate. There is an integer or a number in this domain such that m squared is equal to m. Which one is true? Which one is false? So since we have existential quantifier, it says there is at least one element. If you find that element, you're done. That's enough. There is at least one. Can I find at least one number in the set of positive integers that satisfy this relation? Of course. Since we can find one element, one member in the set of positive integers, which is 1. 1 squared is equal to 1. That's satisfying this predicate. So this statement is a true statement. It is a true statement. Now, what if I restrict the domain to this set? Can I find at least one number in this set that satisfies this relation? Of course not. 5 squared is not equal to 5. 6 squared is not equal to 6. 7 squared, not 7. 8 squared is not 8. So, since we cannot find one element in E satisfying the predicate, so it is false. Question says, translate the following. Well, here we have this universal statement. So we have our domain, which is given as R. I'm not saying that which one is true, which one is false. Just saying that translate. We have a universal, another universal statement. And this is the predicate. C, another statement. In this case, this existential statement. And translate this statement for me as well. All triangles have 3 sides. B, no dogs have wings. And C, some programs are structured. So we can rewrite these in different ways. We can say that any real numbers, any real values multiplied by itself is greater than or equal to 0. For any real number, its square is greater than or equal to 0, or it is non-negative. Here you can just say that any real number, for any real number, its square cannot be -1. For all real numbers, its square cannot be negative. Here you can say that there are some positive integers. There are some positive integers that their square is equal to themselves. So we have different ways of interpreting these or rewriting them in English sentences without using any mathematical symbol. Like this case. Here you have some sentences and you're trying to write them in universal form. So first, you need to talk about the domain. So you can take the domain to be the set of all triangles like T. You can say that for all triangles like T belongs to domain T. T has 3 sides. And T is the set of all triangles. So you have to have your domain. Make sure you write the domain and then express the predicates. So this is a universal statement. You can write that as for any dog in the set of dogs, D representing the set of all dogs, D has no wings. If I take any random dog, of course that dog doesn't happen. Some programs are structured. Some, it means that there exists. You can find some of them. So there are some programs in the set of P, like programs such that P is structured. Perfect. So now we talked about universal statement, existential statement. I expect you to ask, well, what if they have implication? Implication is universal or is it existential? Which quantifier should be used for that? What if we have inverse, converse, contrapositive? So, which quantifiers? If you have Px implies Qx, what are you going to use? You're going to use a universal or you're going to use an existential quantifier. What if you have, for example, the converse? So this is just implication. This is the converse. This guy is the inverse. And if you have contrapositive, not Q, then not P. So for each one of these, you're using universal quantifier. For any x in the domain, px implies qx. For any x in the domain, qx implies px. For any x in the domain, not px implies not qx. For any x in the domain, not qx implies not px. So for implication, we're going to use universal. These are all universal statements. Okay, now another question that I expect you to ask is this. What is the negation of a universal statement? What is the negation for any x in the domain? You have P of x. And what is the negation of existential statement? The negation of existential statement. What is the negation of there is x in domain D such that, for example, qx? How do we negate these two statements? Well, the negation of for any is going to be there is x in domain D such that, so somehow you try to distribute negation over parentheses. So there is x in domain D such that not P. So we have to negate the predicate as well. So make sure you are negating two things. You are negating the quantifier itself and you're negating the predicate itself as well. The same here. The negation is distributed over parentheses. The negation of existential quantifier is universal. So it's going to be for all, for any x in the domain D, not q of x. So we're going to negate two things, not q of x. Okay, another question for you. What would be the negation of implication? Very well. Just be careful here. We cannot directly negate implication. First, we have to convert this into or. So it's going to be the negation of parentheses for all x in D, not px or qx. Then we distribute the negation. The negation of for all, the negation of each of these elements here. So it's going to be there is x in domain D such that double negation, it gives you p of x back. The negation of or is going to be and the negation of qx. I have an example for you. Using multiple quantifiers. Example. I want you to translate these two. The first one says, every non-zero real number has a reciprocal. Every non-zero real number has a reciprocal. And the second one says, there is a real number with no reciprocal. There is a real number with no reciprocal. How do you translate this? Every non-zero real number. So let us focus on this part first. Every, for all, for any, x, which belongs to r, which is not zero. So we're going to write it as r minus 0. For every non-zero real number. It has a reciprocal. What's the meaning of that? It has a reciprocal. There is, so I'm working with the second. There is a real number like y such that x times 1 is 1. So for every non-zero real number, there is another real number like y such that if you multiply them, the outcome is equal to 1. How do you translate the second one? There is, so which comes first? Existential comes first. There is a real number. There is a real number, x, in R, such that it has no reciprocal. If you take any real number, the multiplication is not 1. With no reciprocal. If you take any real number like y, then the multiplication is not